Hello. Time for the last lecture in this section, and this will be the last formula I will derive in this course. And the beginning of this lecture will be very intuitive, and it will be not really hard to understand, but then after the first part it will become kind of hard. So don't beat yourself up if you don't understand everything. It is my purpose just to sketch some facts so that you maybe recognize them later when you study more advanced courses. Let's start. Derivation of a formula, problem number 7. And the first part is about geometry. How to illustrate the geometrical intuition that infinitely many parts can sum up to a finite result. So I will show you a construction which should be pretty easy to understand intuitively. So I will show you an illustration for the sum of these fractions. So you see that it's 1 divided by 2 plus 1 divided by 2 squared, then 2 to the third, and so on and so on. So I understand that what comes later is 1 divided by next powers of 2. And well, you see that I never end this sum. It means that it's supposed to go on forever. So what's the illustration behind this sum? Well, look at this. It represents a unit square. So this is a square with a side length equal to 1. Its area is obviously 1 square unit, right? And I will show you how to divide this square into rectangles with areas 1/2, 1/4, and so on, which will sum up to the entire area of the square. So first, area of this rectangle is obviously 1/2, because this side is 1, this side is 1/2. So the area is 1/2. Then the area of the half of this what is over, after subtracting this first rectangle, is 1/4, right? Because it is 1/2 of 1/2. Then we take a half of this what is left, and the area is 1/8. You can also simply say that it's 1/2 times 1/4. It's obviously 1/8. And so on. The area of this one is 1/2 of 1/8, it's 1/16. Then 1 by 32, and then you understand that we can go on and divide in halves this what is left. And in this way we can say that the infinite sum, so you see I get this sigma sign which symbolizes sum, but this time I go with n from 1 to infinity. I never end this sum. And this example illustrates that the sum of these terms, even if they are infinitely many, is finite, is equal to 1. So here ends the easy part. And now, in the course Pre-Calculus 1 Basic Notions, you can learn more about those sigma and pi symbols, and then you can learn about arithmetic progressions, geometric progressions. So you see there is plenty of exercises there. In this very short course there is really not too much space for exercises. And now I would like to show you at least some sketch of formalization of this result which I illustrated geometrically. So geometric progression is a sequence of this type, that first element is just some number, and the next is the same number times a quotient. The next one is the very first number times the quotient square, then the quotient to the third, and so on and so on. So you see, it could also be formulated in this way, at least if a is different from 0. that the quotient of the next one by the previous one is constant, and of course also if q is different from 0. So the quotient of this one by this one is q, the quotient of this one by this one is also q, you see, because a's just cancel out and q squared cancel out with two pieces of q, so it's just q left. So geometric progression is a sequence in which the quotient of two consecutive elements is constant, equal to this number q. And a geometric series is an infinite sum which is produced as the sum of the elements of such a geometric progression. And now I will show you how to derive the formula for the partial sums of such a geometric series. So you see, if I sum up n, or in this case n plus 1, because you see I start numbering from 0 to n, so they are n plus 1 elements. I can factor out this first element a, and then in the parentheses I will get 1 plus q squared and plus q to the power of n. And now I will show you how to derive the formula for such a sum. And here you will see the entire proof, and the proof will be so similar to Gauss's proof of the sum of arithmetic progression. So what I do first is write down such a sum of n plus 1 first elements. You see 1 plus q squared and so on plus q to the power of n. It's clearly n plus 1 elements because here is from 1 to n and we have one more. Then I can take the same sum and multiply it by this quotient q. And you see that I have strategically written it down in this way so that I get the same elements under each other. You see, if I multiply 1 by q, I get q. Q times q is q squared times q is q to the third, and so on and so on. And this one times q is q to n plus 1. And you may be wondering why I wrote them in this way under each other. Well, because now I will subtract this one from this one, and of course this one from this one. So in other words, I will subtract this equation from this equation sidewise. So at the left hand side I simply get s n plus 1 minus q times s n plus 1. And remember, I try to find out this, so I have to later solve for s n plus 1. And you see at the right hand side, if I perform this subtraction, I will get q minus q is nothing, q squared minus q squared is nothing, and so on until this one. And the only thing which will be left, which has nothing to cancel out with, is 1 minus q to n plus 1. And this is an equation for s n plus 1. And I can solve for this. Of course, this you can do only if q is different from 1. So what have I done here? I have factored out s n plus 1, and then in parentheses I get 1 minus q, which I then can divide both sides with, and then I will get the formula for s n plus 1. It is this number divided by 1 minus q, by this factor which I got here after factoring. So this is my formula. And I can write it here that this sum is equal to a times this expression which I got here with this nice method. And so now we have this sum, and in the future, in Calculus 2, you will learn the following, that such a sequence, if q is less than 1 to absolute value, such a sequence will then tend to 0 with n tending to infinity. If you don't know yet the limits and stuff, don't worry. Just think about it later when you read, when you follow the course in Calculus 2, you can come back here and have a look again. And this helps us establish the formula for the sum of such an infinite series, which will be this number. And this formula is only valid if the absolute value of this quotient in the geometric progression is less than 1. And now if we come back to this illustration which I showed you, then we clearly have a geometric progression with a and q both equal to 1/2, because here you see is this first element, and then this quotient between the consecutive elements is also 1/2. So if you now apply this formula, which I have shown you how to derive and how to understand, then you see that with a and q both equal to 1/2, you get 1/2 here, divided by 1/2 is 1, and you indeed get the result 1. So this geometrical image agrees with this what we can compute. Okay, at the end it was really heavy stuff, so I hope that you enjoyed it. Thank you for watching. Bye bye.